So far, we've talked a bit about concurrency concepts. We talked about how you can program concurrency in Java with threads and synchronizers and message passing. Now let's talk about the dark side of all this, the things that can go awry. And I lump these under the concept of concurrency hazards, things that can go wrong. And we're going to talk about race conditions and memory inconsistencies. And I'll show you the problems, and I'll sort of outline how Java synchronizers can outline and address these hazards in various ways. And we'll also talk about a hazard that stems from using synchronizers themselves. And that's going to be deadlock. And we'll talk about how to address that hazard as well, very briefly. So what are some examples of concurrent programming hazards? So the two of the key ones, there's other ones, but these are some of the key ones, are race conditions and memory inconsistencies. And the issues here is that because we use synchronizers to share resources safely, the reason we do that is to avoid these hazards. So a race condition can occur when a program depends on the sequence or timing of threads to operate properly. Again, it's outside the scope of this class to explain this in great detail. I have other videos that talk about that. But the basic issue here is what happens when you try to read and write from the same shared mutable state, like a field and an object, from multiple threads of control. So let's take a look at an example to illustrate the problem. This is something you can take a look at here on my website. It's called Buggy Queue, and it's an intentionally defective program. It's designed to fail. And here's the Buggy Queue. So what's happening here is we're going to try to define a queue which is going to use an array list as the implementation of some internal data structure. And then we're going to define two public methods, offer and poll. And the idea here is that poll will try to retrieve an item from the queue if it's not empty, and offer will try to put an item in the queue if it's not full. Seems pretty reasonable, right? Doesn't look too bad. Well, the thing to watch out for here is that an array list, which is a very basic Java collection, doesn't care about race conditions. It expects to be used in a context where there's either only a single thread of control, like a sequential program, so there's no issues at all, or it's expected to be used in a context where you properly synchronized access to it. And here's where things can go awry. So if we call offer and poll simultaneously from multiple threads, chaos and insanity may result, because this program depends on the sequence or timing of threads to operate properly. So what's the issue here? If we come along here and we check to see if the queue is not full, and then we add something to the queue, if another thread is removing something from the queue, adding and removing things from the queue mutate the state of the queue, right? It updates some internal fields to add one, and it puts an element into the underlying array list. And if those things happen, quote, simultaneously without being protected by a synchronizer of some kind, then bad things are going to happen, and you're going to get corrupted data. And all you have to do is try running this program, and you'll see it is corrupted very quickly. There's a funny article called Why Shared Mutable State is the Root of All Evil in Concurrent Programs. And they're right. Now, how do you fix this type of problem? There's a whole slew of ways to fix this type of problem. Probably the easiest way to do it is simply to make offer and poll synchronized methods. And synchronized is a keyword that's built into Java since the beginning of time, mid-90s. And that allows the underlying virtual machine to use something called an intrinsic lock, which makes sure only one thread at a time will have access to offer and or poll on the same instance of Buggy Queue. And there's other things you could do. You could use a reentrant lock, you could use the stamp block, and so on. But those are ways that you can fix this problem. Of course, the other way to do it is simply not to have any sharing of mutable state at all, which is what parallel functional programming is all about. But this is what we're doing if we're stuck with concurrent programming. Another problem is memory inconsistencies, and this can occur when different threads have an inconsistent view or inconsistent views of what should, in fact, be the same data. So again, think transporter beam if you're a Star Trek fan, think apparition, disapparition if you're a Harry Potter fan, or just follow along with the discussion if you don't like either of those examples of literature. So here's an example of a program that will induce problems due to memory inconsistencies. So here we've got this class called loop may never end. That kind of gives you an idea what might be the problem here. And you can see it's got a field that's a Boolean field called mdone, and it's got two methods, work and stop work. And this Boolean is unsynchronized, and it's mutable shared data or shared state. And that's because it's going to be read and or written to by these different threads. Boolean fields, by the way, in Java are initialized to false by default, so we don't have to say false. We could if we want to do a belt and suspenders like programming model, which is not a bad thing, but it starts out being false. So imagine that we've got two threads, thread T1 and thread T2, and imagine that they're up and running, and thread T2 is looping, doing some work, while mdone is false, because we want to keep going while we're not done, right? And so it'll just keep looping, doing work. Down here, thread T1 comes along, and it writes to mdone saying, it's done, you're done, stop. I've set you to true. Unfortunately, because there's no synchronization taking place here, there's no memory consistency guarantees. So it may be the case that even though we've updated this field, the processor core that's running thread T2 won't have its cache updated. And that's the way things work in modern multi-core, multiprocessing systems. When you have multiple cores, data is cached in the cores. And the only way that the core, well, one of the only ways that the cores will be flushed to ensure consistency of the memory in the process, in the area that's running all those different threads, is if you use synchronizers or other mechanisms, other means of being able to flush caches. So this program may never stop, even though it logically looks like it should stop. Great example of the subtlety of concurrent programming, where looking at the code at the source code level doesn't necessarily reveal the problems, unless, of course, you know that you have to make sure that you use properly synchronized fields in order to get threads to access and have consistent views of the data. So the easy way to fix this is just to make this volatile, and that will solve the problem. There's other things you could use. There's var handles, atomic booleans, atomic integers, atomic locks, et cetera, et cetera, et cetera. A bunch of ways to make this work, but that's probably the fastest way to do it. Let's talk about programming hazards that can be caused by synchronizers. So this is a kind of a funny one. So ironically, synchronizers can actually cause concurrency hazards. We just saw how synchronizers can remove concurrency hazards caused by not synchronizing, but you can also have problems that occur when the synchronizers are used improperly. And the best example of this is deadlock. So the metaphor here is obviously, hammering your thumb with the nail, or with the hammer, which is self-induced pain. So deadlock is a condition that occurs when you have two or more competing threads that are waiting for the other thread or threads to finish, and thus none of them ever get their job done. That's called deadlock. And here's a classic example that illustrates how deadlock is induced. So here we have two threads, T1 and T2, and two locks, L1 and L2. And for whatever reason, due to the inherent non-determinism of concurrent programming, thread T1 comes along and it acquires lock L1. And now it needs lock L2. But in the meantime, thread T2 came along and it acquired lock L2, and it needs lock L1. And all other things being equal, if you write code like this without taking any other precautionary steps to avoid these problems, you will be stuck in the deadly embrace, where both hold a resource that the other one needs and need a resource the other one holds, and they're both stubborn. Nobody makes any progress. We talk about deadlock in many other contexts as well, obviously, negotiations being a good example, and treaties and so on. So let's take a look at an example. You can see that this is a little bit more programmatically designed, where we have two methods, and they are going to acquire synchronizers on two different types of objects. One is a string, and another is an integer. And so method one is going to acquire the string lock first, followed by the integer lock. Method two is going to try to acquire the integer lock, followed by the string lock. And if they're called by separate threads, T1 and T2 concurrently, then if this guy grabs the string lock and then waits to get the integer lock, and this guy grabs the integer lock and waits to get the string lock, we're stuck back in deadly embrace land, and it's not a pleasant place to be. When you start writing concurrent programs, you will inevitably run across deadlock, and it's very frustrating, and it usually shows up at the worst possible time. There's ways to solve this problem. I'm not going to go through it in detail, but one easy workaround, if you are willing to put the time into it, is make sure that you always acquire locks, if you need multiple things, in the same order. So here, method M1 or method 1 is going to acquire the integer followed by acquiring the string lock. Here, method M2 or method 2 acquires the integer followed by the string. If you do that, then you can work around this problem of deadlock. And there's a whole theory about ordering and lock ordering and so on and so forth, which we will not talk about in this class, but is quite fascinating. And people have written many PhD dissertations on the very abstruse topic of how do you coordinate threads. Here's a program that illustrates deadlock, if you want to see it in full-blown glory. So this is a program that's trying to copy the contents of one queue to the other. And the way it works, the way the program is set up, is that it modifies the source and destination. So one thread is trying to call the source and destination in one order, and the other thread is trying to call the source and destination in a different order or the reverse order, and it deadlocks on itself very quickly. So if you want to see how to write deadlock code, take a look at that program, and then you can always tweak it because it's open source and see how to avoid that by ordering things in the same way, acquiring the locks in the same order. So that's the end of the Java concurrency hazards.